All right. Hello. Welcome back. New change of scenery. I know I also spend most of my time in the science and engineering library. So we're just going to roll with it today. So we're going to be talking about the Biot Savart law. And we're just going to take it as it goes. So I came up with this problem along with Sam today. So this isn't from the book or anything like this, but this is going to be extremely helpful to you so that you can kind of understand how to solve a problem like this. So we want to find the magnetic field at a point P due to the current carrying wire. And we want to find the magnitude and the direction of it. So this is going to be focusing on the Biot Savart law. So let's just write out what that is so we can see what we're working with. So the Biot Savart law says that the magnetic field is equal to mu naught, which is just a constant, over 4 pi. And that's the integral of I, which is just our current, dl cross r hat all over r squared. So that is our problem. That's our equation. And so I really want to focus on this little cross product guy right here and talk about what that means to cross a length element into a unit vector. So yeah, let's just get right into it. So I want to think about this problem, and we have to think about the cross product, because if we look, we want to find our magnetic field at this point P, and we have kind of 3 sections of wire. So let's call this 1, 2, and 3. So the first one is just a straight line in the same plane as the point. So we can kind of see if we just like extend that line, it's going to be on the same plane as point P. And same with 3. But 2 is curved, and we can say that it has some radius. Let's just call it A. So we can imagine that it's just half of a circle and it has some radius A. And so what I'm kind of alluding to is that our magnetic field is only going to depend on the second section of wire and not 1 or 3. And this is because of that cross product right here. So if we want to think about a infinitesimally small piece of wire, that DL. So I'm going to make a little small piece. Let's start with 1. So let's say I have this right here, and it's going this way. That's our DL. And now our R hat is a unit vector. So one more thing to remember is that unit vectors have magnitude 1. So what this r hat vector is the distance from our field point, which is where we're interested in, to our source. So in this case, this P, it would go from our point P to our DL, like that. But again, our magnitude of that is equal to 1. So we don't really have to worry about like values of this. We just kind of want to understand what direction this is going in. So we can see that DL, I kind of drew this a little bit poorly because P isn't exactly perfectly straight, but let's just pretend that it is perfectly straight in line and it's just exactly horizontal to each other. They're just anti-parallel. And so what that means is that for our first part, our DL cross R hat is equal to 0 because the angle between them is 180 degrees, or 0. There is no angle between them. They're right on top of each other. And if you remember, our cross product, we can say, so if we want A cross B, we can say that it's the magnitude of A times the magnitude of B sine of theta, where if we have the sine of theta, we want that to be 90 degrees because that'll give us 1, but our theta equals 0. There's no angle between these two. So for our first part, that dl cross r is equal to 0. So that means that there is no magnetic field from 1 on point P. It's just 0. There's no magnetic field being influenced at 1. And we can do the same thing for 3. So we can imagine that there is this infinitesimally small dl vector, and it's going in that direction. And then we can see that this r vector that I drew is going in the same direction again. So we can say that our dl cross into r hat is just 0. So our b from 3 is also just 0. But 2 is a little bit different. So let's look at that. So now let's look at 2. Okay, so now let's look at 2. So we have our curved surface of radius A, and our dl, let's draw our dl on here first. Let's say it's right here, and it's pointing that direction. So now we want to draw our r vector to the point dl and see what the relationship is. So if I drew my dl or my r vector like that, that's what that would look like. So now let's think about this for a second. What angle are these two at this instant? They're at 90 degrees. So we can say that our dl cross r hat is equal to, it's equal to dl. And that's because it's we can say, so remember, going back to our definition of a cross product, it's the magnitude of A times the magnitude of B times the sine of the angles between them. So dl has magnitude dl, r hat has magnitude 1, and the sine of the angle between them is 90 degrees. So that just gives us dl. So there's that, but we also want to know what direction this is going in before we start solving and doing our integration and setting up our integral. So we can use the right-hand rule to do this. And the way that you want to do that is you want to point your thumb in the direction of the current and curl your hands around it to find the magnetic field at that particular point. So, or you can curl it towards the r vector. So if I have my right hand and I'm pointing it towards the dl vector, I'm pulling my fingers towards me, it's going to go into the board at point P. So we can say that B is going into the board like that. So now we have a nice direction with that too. So now let's solve the actual integral and set it up. So right now we have this integral, and it's in terms of r, but we want to rewrite this to be in terms of something else. Okay, so we want to define our dl in terms of r. And to do that, we want to say, I'm actually going to just going to say that it's r. So disregard the idea that that is with radius A. Let's just call it r. Just keep it simple so that this can just be in terms of general terms. So we want to find our B field at point P. We've already decided that's going into the board. So if we want to define how this is set up, I would say that we could call this y, this is x, this is positive z, and then this is negative z. So we've already decided that since it is in the plane of, it's going into the board, let's say that it has a negative z hat direction. So now let's work on this integral. I want to rewrite dl in terms of r. And so to do this, I'm going to be using the arc length because that's technically what this is. So we know that arc length S is equal to r theta, but we are going to be at the same radius as we go all the way around. So if we look at like a point here, or a point here, we're going to be at the same radius, but our angle around it is going to change. So I want to rewrite this this S in terms of a differential. And to do this, I'm going to say that this ds is turning into a dl so that we are not confused, or that our arc length is going to be r theta, but we want to know what dl is. So since dl is changing, r isn't changing, so we're going to say it's d theta. And so now we have a equation to plug in for our dl to solve for our integral. So I'm going to say that b is equal to mu naught over 4 pi integral I dl. What we're left with from this dl cross r hat is just dl, like we solved right there. So this is just going to be dl, and we found an equation for dl using arc length. So that's going to be r d theta, and it's going to be the same r over squared. And so we can already do some canceling out. One thing to note is that our I is not changing in this sense, so it is a constant. So I can take this out in front of the integral. And then down here, we have r squared, and that cancels out with that r up there. So we're just left with r, and we're just integrating over d theta. So what we're left with is b equals mu naught I over 4 pi integral 1 over r d theta. So it's important to note again that this r, we have no dr in our integrand, so we can also take this out to the front. And now we're just integrating over d theta, so I'm going to rewrite that. Mu naught I over 4 pi r integral of d theta. Now we have to figure out what d theta is and what our bounds are. So I'm going to say that right here is 0. And right here, since we're making half of a circle, I'm going to say that that is pi. So if we do 1/2 of a circle, it's equal to pi. So if you do 1 full circle, it's 2 pi. So half of it is just regular pi. So our bounds here are from 0 to pi. And we are left with b is equal to mu naught I over 4 pi r. And just doing this integral real quick, we're left with theta evaluated from 0 to pi, which is just pi. So I'm going to put another pi right there. These 2 pi's cancel out. And so what we're left with is b is equal to mu naught I over 4r in the negative z direction. So that's great, but let's unpack why I was able to do that. Because I just looked at 1 dl, and as you can see, we have an entire arc. So, and we assumed that at the very beginning that this dl and this r are all, or is going to be perpendicular to each other, like that. But what if I chose a different DL? What if I chose this one? And it went this way. Well, the great thing about circles and how you define your field point, which is this P point right there, is that whenever you pick your R on a circle like this, it is always going to be perpendicular to your DL vector, just like that. So it's pretty cool that this acts that way. And you can utilize this in a whole bunch of different problems. And so, yeah, that is how you would solve for the magnetic field due to a curved wire, just like that. I hope that this was helpful. I will be coming out with another video next week. I know this one's coming out a little bit late, but I will look forward to seeing you guys next time. And don't forget to fill out my math survey that I created and sent out last week. That really would help me to kind of gauge what else I can be doing for you guys. But I appreciate all of the kind comments that you've sent so far. And I'm working on the things that you guys told me I could work on. So yeah, I will see you next week. Have a good rest of your weekend.